Welcome friends, let us go for the extension of the redox reactions. That is, the main importance of the redox reactions is present in analytical chemistry. Whereas there are some technical terms in the analytical chemistry. One is the titration. The meaning of titration is the process of determination of strength. That is, either it may include the amount, concentration, quantity, anything of unknown solution by a process of adding of a standard, that is known concentration of solution with the help of burette, is known as titration. Whereas titrant, oftenly we use the words of for the known concentration as well as the unknown concentration of the chemicals. Titrant, the standard solution, otherwise the solution of known concentration is said to be the known strength, is known as titrant. Whereas the other one is the titrate, the solution whose concentration is to be determined, whose concentration is unknown, whose concentration is analyzed, is said to be the titrate. It is also known as what? An L-8 also. Some more basic technical terms before going to the redox reactions related calculations. Standard solution. A solution of known concentration is known as standard solution, or a solution of known strength, known amount and the known volume is known as standard solution. And once again, this standard solution is categorized into two varieties. One is primary standard solution and second one is secondary standard solution. Then what is meant by primary standard solution is a solution of invariable strength which will maintain its strength as it is, not affected by the atmospheric conditions. Such a solution is said to be the primary standard solution. Whereas primary standard solutions, these can be accurately weighed and their solutions are not to be standardized before use once again. Such kind of solutions are primary standard solutions. Whereas examples for the primary standard solutions are oxalic acid C2H2O4 2H2O solution, potassium dichromate solution K2Cr2O7, silver nitrate solution AgNO3, copper sulfate solution CuSO4 5H2O, ferrous ammonium sulfate ammonium sulfate 6H2O, sodium thiosulfate Na2S2O3 5H2O. Such kind of all solutions are said to be the primary standard solutions. And second is other variety of standard solution is quite opposite to that of the primary standard solution, which is known as secondary standard solution. Solution whose strength is not constant, whose strength is variable with respect to the atmospheric conditions, whose concentration can change, can increase or can decrease under atmospheric conditions by making that one to allow to room temperature conditions for certain amount of time. Such kind of solutions are said to be the secondary standard solutions. That is, solutions are to be standardized before the use, and these are not used as, not weighted, can't be weighed accurately, can't be weighed accurately. Such kind of solutions are said to be the secondary standard solutions. Sodium hydroxide, potassium hydroxide, HCl, sulfuric acid, iodine, KMnO4, such kind of solutions, whatever you made, their concentration doesn't remains constant. Before going to the reaction, once again we have to cross check whether it is maintaining the same concentration or something else of other concentration. Such kind of variable concentration containing solutions are known as secondary standard solutions. In redox reactions, to know about the unknown concentration, unknown strength of the solution, that is titrate related information, we will use a logic that is said to be the law of equivalence, that is law of equivalence is applied. Suppose there is a reaction which is of redox type, one is oxidizing agent, other is reducing agent. Those two substances are, first one is A, second one is B. Then as per the redox reaction related calculations are concerned on behalf of a logic, that is number of equivalences of A is equal to number of equivalences of B. Whereas how number of equivalences are calculated? Yes, number of equivalences are calculated by the formula weight of A by equivalent weight of A. Similarly, the number of equivalences of B can be calculated as weight of B by gram equivalent of B, here weight of A by gram equivalent weight of A. So therefore, on rearranging the things, that is weight of A by weight of B will becomes equal to gram equivalent of A by gram equivalent of B, which is equal to equivalent weight of A by equivalent weight of B. With this logic, the unknown concentration is generally estimated. Classification of types of titrations. The titrations are divided into categories like acid base titrations, in which one is acid, second one is base. And whereas if you are measuring the concentration or the strength of the acid, then such kind of titrations are said to be the acidometry titrations. You know the base concentration, you know the base strength, but now here you are calculating the acid strength is said to be the acidometry. Measuring of acid is acidometry. Similarly, measuring of alkali is said to be the alkalimetry. And second variety of titrations are redox titrations. One is oxidizing agent, second one is reducing agent. And here the basic varieties of redox reactions are Paramanganometry, dichrometry, iodometry, iodometry. These are all are the best examples under redox titrations. And third variety are precipitation reactions, where there is a precipitate formation takes place. Due to that, we have to estimate the quantities of the substances. And the last variety is complexometric titrations. Complexation formation takes place. Due to that is also maybe precipitate, but here complex formation occurs, hence it is a special case of precipitation, that is complexometric titrations. When strength of acid is determined with the known strength of base, then it is said to be the acidometry. Here acid is going to be estimated or acid is going to be determined. Similarly, when strength of base is determined with the known strength of acid, then it is said to be the alkalimetry. Next is, in redox reactions, the first one is Paramanganometry, that is KMnO4, which is a secondary standard solution. We have to once again re-estimate the quantity and the strength of the potassium permanganate present in the solution. Such kind of potassium permanganate can be reacted with the reducing agents. Those are ferrous 2+ salts, oxalic acid, otherwise the salts of oxalic acids said to be the oxalates, and hydrogen peroxide, etc. Whereas it is having pink in color, but after the end point, otherwise after addition of extra 1 drop followed by the end point, here the color changes from pink color to colorless solution. Whereas here the color is due to manganate ion, that is MnO4 minus, and here it is acting as self indicator. It doesn't require any kind of other external indicator while making this one to react with any of these substances. Suppose if I take potassium permanganate in the burette followed by any of the salt solutions or the hydrogen peroxide solution in the conical flask, then what happens is it is having pink in color in the burette. When it is going to be added, the color disappears. At the end point, it persists the pink color. After addition of 1 drop extra followed by the end point, the pink color is persisted. That an indication related to the completion of the reaction. Thereby, the color change is enhanced. Color change is viewed by us. There is no other special extra chemical is needed. Thus, it is acting as self-indicator, and titrations becomes very easy. Sometimes in some of the reactions, acidic medium is used. So therefore, generally the acidic medium used for this potassium permanganate reactions is concentrated sulfuric acid is used. In dichrometry, that is potassium dichromate solution, which is acting as oxidizing agent, this is allowed to react with the ferrous salts, otherwise the iodides, and in this particular reactions, indicator is necessary. Next is iodometry, whereas here standard iodized solution, which is a secondary standard solution, is used, but it is difficult to prepare the iodine solution. Hence, the potassium iodide plus iodine dissolved solution is taken into consideration, which is acting as oxidizing agent, and this on reaction with either thiosulfate, otherwise the sulfite, or with the arsenite, the quantities of the substances are re-estimated. and here indicator is used, and that indicator is starch. Starch is used as indicator. Iodometry, whereas this is a special case. In this, free iodine is not available. Hence, with the iodides, the oxidizing agents are allowed to react in such a way that the limited quantity of the iodide is allowed to react with the excess quantity of the oxidizing agent. The 100% conversion with the iodide as limiting reagent takes place. Iodine formation takes place. This iodine is allowed to react with the reducing agents like sodium thiosulfate, sulfite, arsenate, etc. And in this particular case also, starch is used as indicator. Indicators, substances which gives different colors under different pH conditions are said to be the generally indicators, otherwise pH indicators. A sub-portion of the indicators list. The important indicators that we use are phenolphthalein, methyl orange, methyl red, as well as the phenol red. And the pH range where the color change occurs for the indicators is, for phenolphthalein, in between 8 and 9.8, the color change will occur. In acidic medium, that is lowest pH, that is colorless, whereas in the more than 10, near to 10, the basic medium, the pH of the indicator changes from colorless to pink in color. Whereas methyl orange 3.1 to 4.5 in between color change occurs, and in acidic medium it is having a red in color, whereas neutral, otherwise the low acidic medium, it is having orange color. Still you increase the basic medium, it converts to yellow in color. Methyl red, the pH range is 4.2 to 6.3, and in acidic medium the color is red, and in basic medium the color is yellow. Similarly, phenol red, which is reverse of the above two, methyl orange as well as the methyl red, here in between 6.8 and 8.4 the color changes, and in acidic medium the color is yellow, and in basic medium its color is red. Whereas if you look at the phenolphthalein is having structure like this. In acidic medium it is a complete structure which without having any kind of ionization, whereas in basic medium it needs the donation of the proton. On losing the proton, the structure destroys and it is converted to the other structure, whereas here it is having, in acidic medium it doesn't have any kind of color because it is not have extended conjugation, that's what it is colorless. Whereas in basic medium, after losing the proton in the form of H plus, a conjugation establishes between different benzene rings. As a result, it takes the electromagnetic radiation of visible portion and appears in some other color, and it offers the pink in color. Similarly, the methyl red in acidic medium is having red in color, having structure of complete molecule, whereas in less acidic medium, and it donates the proton in the form of H plus and counterly connected with the cation like sodium plus. So therefore it is less acidic, having orange in color, whereas in more basic conditions the extended conjugation is present and it offers yellow in color. The remaining two indicators, methyl red, which is showing different colors under different pH conditions. Nearby 4.2 it is having some color of red, whereas above 6.3 it is having color of yellow. The corresponding structure of methyl red is like this. It is nitrogen-nitrogen connectivity with the double bond, followed by nitrogen with the two methyls, and the another one benzene ring is having carboxylic acid. In acidic medium it is having red color, whereas in basic medium it is present in the form of carboxylate and having yellow in color. Similarly, the last variety of the important indicator is phenol red, which is having the corresponding colors in acidic medium as yellow, basic medium as red in colors, having corresponding structure similar to that of the phenolphthalein. Instead of this here carboxylate, here sulfate structure is there. In acidic medium it is having yellow color, that is molecular form, whereas in basic medium it is present in the ionic form after losing H plus. Here H plus is donated and it is having red in color. Thus, the pH will influence the ionization of the indicators. As a result, they shows the different extension of the conjugation. Due to this different extension in conjugation, they shows different in colors. Thus, we will sense the colors from the outside. Hence, these materials are used to identify the end points, and these are known as indicator materials. The next very important compound is equivalent weight. Now we will define what is meant by gram equivalent weight. Then similar to that of the atomic weight, that is gram atomic weight, relative atomic weight, and the exact atomic weight. In the same way, equivalent weight is also having the definitions like gram equivalent weight, exact equivalent weight, and the relative atomic weight. So it becomes easy if you go through the proper definition of the gram equivalent weight. The weight of substance in grams that can either combines or replaces 1.008 grams of hydrogen, whereas in terms of volume, that is 11.2 liters of hydrogen gas under STP conditions with respect to hydrogen. Similarly, with respect to oxygen, either that can combines or replaces 8 grams of oxygen, that is 5.6 liters of oxygen under STP conditions, or with respect to the chlorine, either that can combines or replaces 35.5 grams of chlorine, that is 11.2 liters of chlorine gas under STP conditions, is known as its corresponding gram equivalent weight. Why we are defining this particular gram equivalent weight in terms of hydrogen, oxygen, and the chlorine is, these are the very reactive elements. Every particular atom or every particular element or most of the compounds are generally combines with these particular elements. So therefore, on behalf of reactivity, these are taken as reference to define the gram equivalent weight. Let us have an insight into the definition. Suppose hydrogen, generally hydrogen is present in the form of H plus, oxygen is present in the form of O minus 2 in the ionic form, and chlorine is more electronegative. First of more electronegative is oxygen, then chlorine, that is present in the form of Cl minus. Whereas the 1.008 grams of hydrogen is consisting Avogadro number of hydrogens. Avogadro number of hydrogens related weight is 1.008 grams. Similarly, here oxygen generally in the form of ion, it is present in the form of O minus 2. So therefore, it is having charge of di negative charge. So therefore, half of the Avogadro number of oxygen atoms weight is reckoned as reference because it is producing Avogadro number of electrons, Avogadro number of active species. That is 8 grams of oxygen is responsible for the Avogadro number of active species, that is Avogadro number of electrons. Similarly, if we take 35.5 grams of chlorine, which is consisting Avogadro number of chlorine atoms, whereas generally chlorine is present in the form of Cl minus, that 35.5 grams of chlorine is right enough to exchange enough the Avogadro number of active species. Hence, this particular weight is taken as reference. That is, either that can combine or replaces 1.008 grams of hydrogen or 8 grams of oxygen or 35.5 grams of chlorine, or in terms of volume 11.2 liters of hydrogen, 5.6 liters of oxygen or 11.2 liters of chlorine. Such kind of weight equivalent is said to be its corresponding gram equivalent weight. Thus the definition, once again in more generalized form, the weight of substance that is responsible for production of Avogadro number of active species. Avogadro number of active species, the meaning is Avogadro number of electrons exchange. Avogadro number of active species exchange relevant weight is said to be its corresponding gram equivalent weight. Whereas in terms of hydrogen, it will becomes equal to the weight of substance that can combines or replaces 1 gram approximately, otherwise 1.008 grams of hydrogen, 8 grams of oxygen or 35.5 grams of chlorine. Equivalent weight, reactive amount of substance, either that can with these or these or this is said to be its corresponding gram equivalent weight. Now let us go for the example. Suppose if I take aluminium, yes, aluminium that can readily combines with hydrogen, combines with oxygen, combines with chlorine, and it can form aluminium hydride AlH3, and it can form aluminium oxide Al2O3, and it can form aluminium chloride AlCl3. Whereas suppose if I take the 1 gram of hydrogen, yes, if I take 1 gram of hydrogen, if I take 8 grams of oxygen, if I take the 35.5 grams of chlorine, then the corresponding weight of aluminium that is reacted with this, suppose if this is 1.008 grams, and this is 8 grams, and this is 35.5 grams. These are the weights. In order to combine with 1 gram of hydrogen, the weight of aluminium required is, yes, here it requires 9 grams of aluminium, because AlH3 is there. The total molecular formula corresponding the weight percentage of aluminium, if you calculate, that is 9 grams, because the total molecular weight will becomes equal to, here aluminium 27 plus 3, 30. Out of that 30, here 3 is the weight of the aluminium. So out of 30, 3 is the weight of aluminium, 27 is the weight of, 3 is the weight of hydrogen, 27 is the weight of aluminium. If I take hydrogen as 1 gram, so within that 1 gram proportionation related weight is 9 grams, hence gram equivalent weight of aluminium is 9. Similarly, with respect to oxygen also, if you calculate as per the molecular formula is concerned, here it is 27 into 2, 54, and here it is 16 into 3, 48 is there. But if I take 8 grams, and this will become 1/6, and once again it will becomes equal to 9. Similarly, in case of aluminium chloride, the corresponding weight ratios, if you take, the amount of aluminium consumed is 9 grams, and the 9 grams is said to be the gram equivalent weight of the element. Here the element of the substance is aluminium. The weight of substance, either that can combines or replaces. Here it is combining 1.008 grams of hydrogen, or 8 grams of oxygen, or 35.5 grams of chlorine is known as its corresponding gram equivalent weight. Equivalent mass of an acid, that can be given by the molecular weight of acid divided by its basicity. Basicity is the number of hydrogens that it can donate in the chemical reaction, is said to be its basicity. It varies as per the reaction is concerned if it is maintaining more amount of basicity, but generally basicity remains constant. So we are taking here the generality into consideration, not going for the extremes for the discussion of the exceptions. Whereas some are monobasic acids, some are dibasic acids, some are tribasic acids. So we are considering the maximum basicity. These are all are the acids: HCl, HNO3, hydrochloric acid, nitric acid, sulfuric acid, acetic acid, oxalic acid, phosphoric acid, phosphorus acid, and metaphosphorus acid. And these particular acids are having corresponding basicity. Donate 1 proton, it can donate 2 protons, it can donate 1 proton, it can donate maximum 2 protons. Here it is 3, it is 2, and it is 1. The corresponding basicities are here, and corresponding molecular weights will be 36.5, 63, and here it is 66. And the gram equivalent weight is the molecular weight divided by basicity, hence it is 36.5, and here it is 63 as it is. It is half of molecular weight, 98 by 2, that is 49, and here it is 60 by 1, 60, here it is 126 by 2, that is 63. This is 98 by 3, 82 by 2, 66 by 1, 66. These are the equivalent weights. Whereas if you want to represent the gram equivalent weights, we will keep the word gram over here. That will be the gram equivalent weight. And exact the equivalent weight will be given by this much of AMU, 36.5 AMUs, 60 AMU. Whereas exact equivalent weight is responsible for one active species. Whereas the gram equivalent weight is responsible for Avogadro number of active species. In case of acids, that active species is H plus. That is the weight of substance that can capable of, that is having strength of producing Avogadro number of H plus ions is said to be its corresponding gram equivalent weight. Next is equivalent mass of base, otherwise equivalent weight of base, that will be given by the molecular weight of base divided by acidity, whereas acidity is the number of OH minus ions coming out of base is said to be its acidity. Some of the bases are monoacidic bases, produces only one OH. Some of the bases are diacidic bases, produces two OHs. Some of the important bases regularly used in the laboratory, sodium hydroxide NaOH, it can donate only one OH. Potassium hydroxide KOH, donate only one OH. Ammonium hydroxide can donate one OH. Calcium hydroxide can donate two OHs. So therefore corresponding the molecular weights, sodium hydroxide 40, potassium hydroxide 56, ammonium hydroxide 35 and calcium hydroxide 74. The corresponding division with the basicity offers 40 by 140, 56 by 156, 35 by 135 and 74 by 2, that will becomes equal to what? 37 is the corresponding equivalent weight. Once again here also, if you want to know the gram equivalent weight, and this will be 40 grams and this will be 37 grams. If you want to know the exact equivalent weight, yes, this is 40 AMU and this will be 37 AMU. Once again here, relative equivalent weight is a number, whereas the relative equivalent weight in terms of AMU is said to be the exact equivalent weight. Relative equivalent weight in terms of grams is said to be the gram equivalent weight. Gram equivalent weight will produce as Avogadro number of active species, that is Avogadro number of OH minus S, or in broad sense Avogadro number of electrons. Whereas here the exact equivalent weight will produce as one active species, that is one OH minus ion, that is capable of producing or capable of exchanging one electron. Yes, equivalent mass of salt, that can be given by total mass of salt by either the total charge present on the cations or the total charge present on the anions. Can be given by total number of positive or the negative valencies present on the radicals with the same meaning. Suppose different varieties of salts, sodium carbonate is there, ammonium chloride is there, silver nitrate, barium chloride, calcium carbonate, sodium chloride, etc. Whereas the total charge of either cations or anions, 2 units of positive, 1 unit positive, 1 unit positive, 2 units positive, or you may take negative charge, 2 units negative, 1 unit negative, like this. Whereas the corresponding formula weight, gram formula weight, otherwise formula weight is 106, this is 53.5, 170, 208, 100 and 58.5. The corresponding equivalent mass can be given by 106 by its corresponding charge, either on cations or anions, by 2, that will be 53, and here 53.5, so 170 as it is, here the charge is 2, so therefore 208 by 2 equal to 104, 100 by 2 is equal to 50, 58.5 by 1 is equal to 58.5. This is the equivalent weight, whereas gram equivalent weight can be given by the corresponding grams, whereas the exact equivalent weight can be given by corresponding AMUs.